Hello, everyone. How are you? Oh, good. Well, that's not... No, it is. You're right. It has been very hot today, hasn't it? They say one of the hottest of the year. But anyway, that's enough of that. Now it's time to move on to science. This is our regular Sunday science Q&A. And today, sometimes we have kind of specific themes, but today it's kind of a little bit more of a hodgepodge, which is more fun for me because it means that I undoubtedly always go to the wrong person first, who then says, I think you'll find Brenna is probably better. I think you'll find Helen. I think you'll find John, etc. So a lot of that's going to happen. That is today we have author and one of the trailblazer pioneers, Brenna Hassett. We have the man who did a wonderful link up live with CERN some time ago. Oh, by the way, just here's my show and tell. I don't know if you can see my show and tell. There, that's my show and tell. Not mine, but nevertheless, something of a camera hog. So obviously by nurture, not nature, that dog's picked that up for me in the last 2 weeks. But we also got Jon Butterworth, who there was a wonderful time where Jon Butterworth is, I think, still. Are you back at UCL, John?
Well, I'm in Kentish Town, actually, but yes, UCL, technically.
Oh, my God, that dog tells me, by the way, and it smells. I am going to have to change what it eats. It's one of the lucky things, actually. I have a nice life of mixing with a lot of different people, and I've just received an email from an astronaut telling me about how much their dog is breaking wind at the moment as well. So there's something going around. But yes, John, who's written 2 fantastic books about helping us understand the laws of the universe, and in particular also the Large Hadron Collider, and obviously we're joined as usual by Helen Czerski as well. How are you, Helen?
I am doing very well. Warm as like everyone else, but yeah. Enjoy. I'm forever too cold. So I never complain when it's warm. So in the middle of winter, then I'm just the one in the corner who's like, but I'm cold all the time. But this is brilliant. I can live in this weather. And I have a show and tell which is ice based, because I thought that would cheer everyone up. Just the reminder that ice exists. But I don't know what it. The problem is none of us know what it is. So it's this is a picture that hangs on my wall. There's lots of them. They're all sort of quite similar. And this is the picture of the inside of an ice floe from the North Pole, and each one of these is about 5 millimeters long, and that they're little holes in the ice. So we're looking through clear ice, and inside the ice there's these little spherical holes, but they've all got a little pointy bit out the top. And a friend of mine, Mario Hopman, took this picture in this beautiful ice, and we all agreed that they were very pretty, and then we also all agreed that nobody had any idea what they were doing there. So if there are any ice scientists out there, then this is quite nice. But I keep it on my wall because I quite like not knowing what it is. And I quite like that the fluid dynamics of it, because ice is really complicated stuff. You know, it's sort of it doesn't stay put. When it freezes, if there's pressure and as the stresses on it change, it doesn't quite melt, but the molecules move around, so it changes shape. And I think this is a result of that process, that it froze once, and then whatever happened to as the temperature cycled up and down a little bit, water molecules moved around and they form these little holes. So they're like inverse Christmas tree baubles. You know, that's an absence and not a presence. So I just think they're quite pretty. So I thought I would show that to everyone because it's quite nice. Mysteries that are still out there. And of course, that ice will have melted now. So maybe we'll never find out what it was.
And of course, there's also that everyone there should be criticism by physicists. Let's have a look at the way that Magritte has used the fluid dynamics to create the surreal image of the man. I will quickly, before we do the show and tells with Brenna and John, I will mention that this week we have on our show and tell Jay Wilgoose from the fantastic Public Service Broadcasting, who one of my favourite bands. And if any of you were able to come to, I think it was 3 years ago when one of our Compendium of Reasons at Hammersmith, which currently is still meant to be happening in December. I have no idea. I don't think we're putting any more tickets on sale for the time being, but it's still officially happening. But we had them on. They opened the show and Duran closed it, and it was a lot of fun. And Jay Wilgoose is going to be talking about some of the things that he has collected and particularly excite him and interest him. And of course, if you know the music and you know the broad different ideas that they've dealt with, from kind of the manufacture of Spitfire to the Apollo missions to mining communities in Wales as well. It's an incredible album, that, with some really brilliant sampling as well. Then it will be quite a delight, I think. And also we have the new Genetics Shambles podcast, which will go up on Wednesday night. We've had a lot of interesting conversations over this week with geneticists covering a huge amount of ground of both the future and the past, and somewhere in the middle ground of the now as well. And next Sunday's show, I should also tell you, is Jen Gupta and Katie Mack. You may well have seen Katie before. Here's a nice spread actually about her in the Observer today, her excellent book all about the different ways that the universe may well come to an end. It's a very upbeat conclusion to the universe with some really quite absurd but apparently equation-based possibilities as well. And I'll also mention our tip jar. We have a tip jar at the bottom somewhere on your screen. If you're able to leave a tip for this show, that is fantastic. And if you are able to actually donate to Cosmic Shambles Patreon, that makes a huge difference. We very much kind of hit a plateau with that. We are very aware that, of course, at the moment there are an enormous number of people creating stuff online and asking for your money, but many of them will not use it wisely, whereas we use it to improve human civilization and our understanding of it. But yeah, we're still making about 3, 4, 5, sometimes 6 shows a week, and we're making them on next to nothing. And of course, a lot of people kind of involved in our projects have no other work at the moment as well, because I don't know if you. Most things are closed for the performer at the moment. So let's get started. I will talk about your books later on, and also
I've just realised, Robin, that I should apologise because I did a very scientist thing there, which is that you said hello. How are you? And I went, oh, science.
No, that was absolutely fine.
That maybe wasn't what you were expecting.
Show and tell, which is I just found on my 21st birthday, someone who's particularly tight gave me this cassette of Tom Jones. There we are. It's one of those ones that says it's not unusual, but then the rest of it is very much not the ones you'd choose. $1.99 Woolworths. Thank you, whoever that was.
Have you ever taken it out of the box? That could be a valuable. If you've never touched it, that could be a valuable. That could be a valuable artifact now if it's pristine condition.
Classic contour label. There's the if you're wondering what was on the spread there inside, there we are. That is it. Draw on it. It does have With These Hands, which of course is very well used in the movie Edward Scissorhands. So, Brenna, what is your show and tell? I'm expecting something exciting from your show and tell, because you are. Whereas with Jon, I'm always worried because he's not allowed to take a lot of his work home with him. You hopefully are allowed sometimes to take some of your work home with you.
We do actually have pretty strict rules about taking dead people home with us. There are for a number of probably quite good reasons. Fear of instant resurrection, zombie apocalypse, etc. But also, like ethics and stuff. Plus, you've stolen my thunder with your archaeological artifact. But I thought, given that I believe you've been having some dental issues, and it turns out that I actually have a PhD in dental anthropology, which is a real degree that you can get if you don't do anything else worthwhile with your life. So I thought I would bring you some plague teeth.
Oh, great.
I mean, that's what we want to know about, right? Is teeth. So Robin, I think you've got basically a tooth that has decided to self-destruct. Is this what I understand?
It's kind of a homeopathic tooth. It's a tooth with a memory of a tooth, which is kind of trying to rely on that memory to create some kind of integrity of structure, and it's failing.
So it turns out you are actually entirely right about the memory thing, because of course, my entire goal in this life is to convince everyone that your teeth are fossils that are inside your head, because your teeth grow one time. That's it. Your tooth has not spontaneously regenerated?
No, I don't think so.
No. And, I got to say, it won't. I'm very sorry. But so, if you think about limbs, if you've ever broken a bone, most people have at some point had the joyous experience of, snapping an ulna or two. But they fix, right? They knit. Because your bone is a living tissue that sort of constantly regenerates. Basically, depending on which bit of bone, there's really no part of it that's older than about 11 years. That's how fast the turnover is. So if you're knitting back bones, great. However, if your real interest is to find out what happened to those bones through life, then remodeling sucks. So if you're like me and you just wish to dig up a dead person and have an intact record of everything they've done in their life, what you actually want is teeth. Teeth grow once, you chip them, you rot them, and they are gone. But the nice thing is they grow nice and regular, and they basically form a fossil. So they capture every little bit of everything that went into them while you were growing them. So everything you fed your kids, everything you were fed as a kid, is locked into your teeth from about 20 weeks pregnant onwards. So starting inside the womb, you have a beautiful little chemical and physical track record of every bit of your growth, which of course you have now ruined, which is, unfortunate for future scientists. But
well, presumably not though, because presumably I don't know about Robin's tooth, but one thing that happens to people in dentists sometimes is that they have their teeth taken out and then they can look at them. Presumably yes. That means you can read your record while you're still alive.
Yes. So again, the ethics issues, it turns out that there are laws about experimenting on yourself that actually apply to whether or not it's legal to donate your own tissue or those of your children. So like the project I work on has to have very serious medical ethical clearance. It is called the Tooth Fairy Project, and I feel like some children were possibly misled.
So let's have a look. Let's have a look at these plague teeth of yours.
Right.
Then.
Well, so what we actually have is the ghost of plague teeth. This is Liverpool Street Station, 1985, massive construction site. Do you know what's under Liverpool Street Station?
Teeth.
Dead people with their teeth. Massive, massive plague pits. Turns out plague is kind of a human thing. Like, we do it a lot. Turns out if you're going to move all those people together and maybe not make some of them as healthy as other people, you're going to have a plague. And Liverpool Street Station, when they dug it up, they started finding like thousands and thousands and thousands of bodies. There were bodies everywhere. And apparently, every time they dug up, it used to be Broad Street Station, then it was Liverpool. Every time they dug up, try to move a road, try to put something else in, there would just be piles and piles of bodies. Turns out a lot of these were basically plague pits. And what we want to know about plagues in the past, and this is someone called DeWitt, who's done a lot of work on this, is very cool. But basically, we want to know, what makes you die in a plague? Why me? Is kind of the scientific question there. And one of the things we can ask is, if we look at all of the teeth that recorded all of this stuff from when you were growing up, what you were eating, how fast you were growing, how healthy you were, if we look at those teeth and we look at them and say, oh, some of these teeth look like they belong to kids who really had sucky lives, and we look at the dead people in the pits, we can ask, did having a sucky early life lead you to die in a plague pit? So we take little tiny casts of the little tiny teeth, and we actually use them to look at every single time a kid in the past stopped growing. Because your teeth are a fossil, right? So they're growing, growing, growing. Something shuts down your body, fever, malnutrition, particularly scary dream, we don't really know. It leaves a line in the tooth. If I take a cast of your tooth using an exciting series of dental molds, I can actually use a microscope to look at those lines, figure out if you had a sucky childhood, and then look at your body in a plague pit and say, oh, well, that kind of predisposed you to dying in a pandemic, didn't it? So what I have here is actually the green gooey mold, which is where we would pour in an epoxy to make a beautiful cast of these teeth. And then, this is where it gets really exciting, we would coat it in gold.
That's just showing off.
It is also, you know what you can't see is clear epoxy. That is really difficult to see. So this is our shiny, shiny gold tooth. I'm hoping it shows up.
Yeah, it does.
And on that shiny, shiny gold tooth, there are lots and lots of little tiny lines. Where there's a big fat line, that's where growth sucked. That's where growth stopped. And so it's my job to count that up under either an SEM or another high-powered microscope in order to tell you that, yes, having a sucky childhood predisposes you to dying of plague.
Brilliant. That is a very upbeat start. And I rather like the mould that you used there as well. The green had a look as if it was a scale model of, I can't remember if they were selenites or not, from Hobbs End Station at Quatermass and the Pit. So it has a kind of still, for those of you who have probably the best in the Quatermass Hammer series. Jon, 2 questions. Is your show and tell a cat?
No, it's not. Why? No, it's not. Why do you have
a cat? I was trying to work out if someone has a cat. I can hear the sound of a cat, but I might have cat tinnitus.
I can't hear.
That might be my fan.
Oh, there's an element of the sound of a kind of a snoring creature, but it's not you, John. That's good. So, John, what is your show and tell today?
Okay. Yeah. So no teeth, I'm afraid. It's this. So this is a little model, a scale model of a dipole magnet from the Large Hadron Collider. Because I'm a bit of a one-trick guy. That's what I do for the Large Hadron Collider.
It's a good trick, though. 27 kilometers, the length of the circle line kind of, colliders go. Yeah. I feel if you're going to have one trick, pick an enormous collider as your trick.
Right. Sometimes I feel I'm milking it a bit, but fine, good. I'm glad you like it. So this is what this is. It's merchandise, right? So, but I don't feel bad about it because the CERN is not allowed to sell this stuff online. So if you go to visit CERN, you might be able to buy this in the shop, but it's not. They're not allowed by treaty to make a profit out of it. So I'm not really doing anything corrupt here. But it's the phone charger. You see, it's got a little USB things, and it stores 1% of the energy that one of the real dipoles will store. So that's that. But the thing I'd also like to show about it is if you look at the end of it, it's kind of structurally true. So there's a little kind of two. You see, it's not just like one hole through the middle where this is where the beam goes. It's one of the real thing bends the proton beam in the Large Hadron Collider, makes it go around the corner. Okay, so it's really powerful. There's a figure 8 in there, and there's a story behind the figure 8 that I'd like to tell you. This little double-centered thing, right? So when they were planning to build the tunnel that the Large Hadron Collider is now in, they actually built it for a machine called the Large Electron Positron Collider, LEP, which ran in from 1990 to 2000. Same tunnel, 27 kilometers, huge tunnel. But they had in their head that we would probably like, after we've done that experiment, to put protons in the same tunnel. And the people who built the magnets at the time said, well, you need to build a tunnel bigger. Then instead of it being sort of like the northern line, it has to be more like the circle line. It has to have a bigger bore, this tunnel, because otherwise we won't be able to fit the magnet in to their protons. You can build the LEP needed less powerful magnets, and that's why it was easy to do that first. So they said, but you can imagine 27 kilometers of tunnel. If you want to build the tunnel 1.5 times the diameter of the tunnel, that's a lot of money. That's a serious investment, right? So they argued about this a lot. They said we could build a tunnel and it'll be useless in 10 years, or we could build a tunnel that'll keep us going for decades, but it'll cost 4 times as much or something. So what are we going to do? And they compromised, in typical CERN compromise. They said, we'll build it a bit bigger, and then you guys have got to work out a way to make the proton magnets smaller. So instead of having 2 completely separate beams, one for the proton one way and one going the other way, you have to integrate the magnets. And that's what that figure 8 is. So one of the protons goes in one of the holes of the 8, and the other goes in the other hole of the 8. And the whole magnetic field polarity is set up so that you have the right sign of field bending one going one way and the right sign of field bending the other going the other way. And that meant they could fit it all in a tunnel that was not much bigger than they needed anyway for LEP. So it was affordable and justifiable. And that's why we have the Large Hadron Collider in there today, rather than needing a completely new tunnel to build it. So I really like the long-term. This was in the 80s, right? They were doing this. And they didn't know how to build the magnets then. They were just saying, we reckon by the time you start building the LHC, you'll have sussed this out, guys. Go away and work on it. And meanwhile, we'll do the tunnel. So having just been involved in a 2.5-year European strategy for particle physics process with the kind of talking about what might happen in decades in the future, I really like the example that it can actually work. It's like these people building, whoever planted out carefully for my grandchildren. It feels a bit like that in particle physics sometimes, but that's what you do.
That's what I like. I mean, I see it very much as the Brookside Close of particle physics. It's not merely a film set. It's also going to be eventually available for housing as well. So we have very you would always go and see the live opera. Me always being lured by soaps of the 1980s. Right, we have an enormous number of questions. And just a reminder, I'll mention as well, in fact, your books. Your most recent book, I think, is Map of the Invisible, John, isn't it?
Correct.
And Brenna, I think your most recent book is Built on Bones. I hope that is correct. And Helen has joined that wonderful group of people who've made rather beautiful ladybird books as well, of various different scientific ideas. And she has a ladybird book as well, all about bubbles. So there we go. That's your crass commercialism over and done with. We will attempt some crass commercialism again in about 20 minutes. So we're going to start off with Daryl Easterly, right? He's got a morbid question. But if future civilizations dig us up in 200 years, does Brenna think we will be able to tell if the bones were of a person who had COVID-19 in the same way as talking about plague? And that's a kind of just builds up from what you've been talking about.
So bioarchaeologists hate plague. I mean, for all the normal reasons. But anything that kills you fast and doesn't affect your skeleton is extremely annoying for people who dig up dead people. Because essentially, if you just have like a little virus or little bacteria, it's going to go through you, it's going to dissipate into the soil, we're never going to find it, and we're never going to know. Since we've gotten better at like DNA and little tiny microsampling, we can now kind of find some bacterial DNA that's like trapped inside bones, so we know that was the thing what done it. So we can find bubonic plague inside bones now. But something like a coronavirus, I mean, I hope we're better at this in 2,000 years. Let's go with I hope we're better at this in 2,000 years.
So this is good. Well, we'll get on to something that biology, of course, always very messy. So instead, we're going to go to you, Jon, now. And this is, I warn you, this question includes quotes from you in The New Scientist from last month as well. So let's hope. Yeah, it might be in the month before. I think it's apparently it's the I like specific questions. This is from an interview from the 16th of June, 2020. Jon Butterworth was talking about the Higgs and Standard Model and saying that its health is disgustingly good and we need to find deviations. Where could these deviations come from, and what new bits of kit could help with that?
Okay, good. It's quite a broad and on-point question. So I guess even before answering that, you might say, why do we need to find deviations? And the reason for that is that there are big chunks of physics that the Standard Model doesn't explain. So it's like we don't understand what dark matter is. We don't understand where all the antimatter in the universe went. So those are the reasons that and that's not understood in the Standard Model. So we would like to find deviations, little things that go wrong, that would be a kind of loose thread of the Standard Model that you can pull out and maybe gain some deeper insight into the rest. So when I say it's disgustingly healthy, that's why I'm kind of disgusted, because there's no little threads that we can see that are that loose at the moment. There are actually some things that may turn into loose threads if we pick at them hard enough. An experiment at CERN, which is not my experiment, LHCb experiment, has got some weird-looking anomalies in some rare decays, which may be a sign that that electrons and muons and taus, which are the three kinds of leptons, don't behave the right way. They're expected to behave the same apart from their mass. And there are some hints that they're not doing. And then none of these is totally compelling yet, but they're kind of all beginning to point in the same direction. They're like a lot of straws blowing in the wind, but they're all kind of blowing in the same direction. So maybe it actually is a wind that's blowing them. And likewise, the thing that broke the Standard Model, or at least caused it to be modified, is the neutrino. We thought neutrinos had no mass, and we now know they do, but we don't know what the mass is, and we don't really understand the mechanisms that generate it. In that case, it may or may not be to do with the Higgs. So I think the short answer is that the lepton sector is interesting, which by leptons, they're the lighter particles. So the electron is the most common one, but neutrinos and muons and taus. And in general, it's to do with flavor physics, we call it. It's the different flavor is just the label we give these different particles. And that seems to be where the material of the Standard Model looks raggedest at the moment. And there are experiments coming online both at CERN and in Japan and in North America that will give us significantly more data about that. And if we're lucky, then some of that will turn into something concrete that may actually give us a clue to what the bigger, better theory that contains the Standard Model is. So that's where I am at the moment, but it is very much on the speculative, it's the frontier of knowledge. So that answer may change in a few months, but that's where I would put my money at the moment.
Brilliant. Thank you very much. Now, the next question has got fish in it, so I'm going to ask you, Helen, because obviously we know anything undersea. I'm not entirely sure I understand this question, but that's my own stupidity. This is from Adam. Adam says, how far can electricity travel? E.g., if you put a battery in the sea, can fish feel an electric charge?
Okay, so this actually is interesting. So electrosensing isn't common in the biological world, but there are some things that can do it. Platypus can do it, and sharks can do it. Sharks and rays. So that group of fish, and they are fish, can electrosense. The thing that is generally true is that those kind of electric and magnetic fields don't travel very far. They don't exist for a very you don't have to go very far from the original bit before you get away from their influence. So, for example, one thing that people do to repel sharks or to attract them, used in different ways, is to put things that have electric currents going through them. In fact, I've had science experiments that if you put them in the ocean, because they've got an alternating electric field, the sharks will come and nose around them and want to know what they are. So they can definitely sense electric fields. It doesn't work if you have something like a battery, because effectively the ocean is a conductor. It's full of salt, it's brine. So basically it just connects up the battery, and the battery will drain very quickly. Also it will rust, and all other things will happen. So you don't get, if you just drop a battery in the water, it doesn't generate enough of anything. But if you have a constant power source, like a living thing, so that's why a lot of these fish, these elasma branch fish, can sense them. It's because living things produce electric fields. And if you're a ray and you're scooting over the ocean surface and there's something just in the sediment down here and it moves, you can detect it. And there's one very other interesting thing of this, which is still the science behind it, as far as I can tell, seems to be robust, but no one's quite worked out how they use it yet. Is that one of the things that happens is we know that if you move a conductor through a magnetic field, you get electromagnetic induction. So you can detect a voltage if that's what you're doing. And of course, the Earth has a magnetic field, and that magnetic field extends into the ocean. So it's thought that there are underwater animals that as they swim through, and sharks are some of these, they swim through that magnetic field, they can sense, because they have conductors inside them, they can sense the direction of the magnetic field, and that might help them navigate. So it's a hard thing to test. I don't know all of the details of the way it works. So basically, yes, fish can sense electric and magnetic fields. Some fish, not all of them, because you need the right electronic component effectively inside you, which is a fluid-filled tube. So the sharks and rays can do it, and but it's not a long-range force. It's not a long-range sensing skill, except the ones that might be able to use the Earth's magnetic field to just get a hint of which direction they're pointing in. So the answer is sort of yes and sort of no. And John's got his hand up.
Please, John, yes.
Yeah, sorry, I just wanted to add a slightly possibly confusing and contrarian thing, is that actually light is an oscillating electric field. So insofar as fish can see over long distances, they can, actually the ocean attenuates light as well eventually, right? But it's not really what the question was asking, but it's maybe worth mentioning that light is actually an oscillating electric field. So that bit of electric fields many animals sense, including us.
Brilliant. We've got a question now. We're going to move straight on to diet. And I wish everyone else could see this. Unfortunately, I can see everyone, whereas you at home can only see whoever's talking. And if only you knew that in between answering questions, John is currently enjoying a lovely orange lollipop, which he's being really careful. I saw him listening. He's having one of Ice Kitchen's lollipops. And I saw him listening to Helen's answer. And I could see him go, I reckon she's got at least 3 more sentences. I can have another bite. We will try and catch him out with his lolly shame a little bit later on. Now, this is this question from Carl White, and I'll give you this to you, Brenna. This is the question is, what are the benefits of the paleo diet? I'm baiting a little bit, but I still see so much nonsense about it online. So tell everyone a little bit the paleo diet, what it is, and then the benefits.
Right. So paleo diet, I'm going to start off with saying it's pretty much the bugbear of anyone who works on Paleolithic archaeology. So the paleo diet is the idea that we are not adapted to eat certain foods, that things that we probably developed later, like pot noodle, are not, in fact, sort of our evolutionary sort of target, and that a lot of diseases and health problems could be fixed if we just went back to eating what our cave people ancestors ate. So
quick cut to John eating his lolly.
Oh, you missed
it wasn't
it.
fast enough. He missed it. Damn.
I'm not ashamed. Here it is.
So it turns out, so the thing with the paleo, so the real paleo diet is not starving to death. That is literally all it is. That is the actual definition of paleo diet. Congratulations, you lived and reproduced. Well done. So I mean, actual, people in the far distant past, hunter-gatherers, they ate porcupine, they ate turtles, they ate anything they could. I mean, we have ethnographic evidence from modern hunter-gatherers that show their diet, like 15% of their calories come from honey. Like we are not a sort of abstemious species. So the thing with paleo diet, it's like, if it makes you feel good and you can afford it and you can still not get scurvy or basically what's called rabbit starvation from only eating lean meat, if you can get enough nutrients in you, great, do it. But it's not a real thing, the paleo diet thing. We have evolved to eat things and live. I mean, milk eating. A lot of people can't have milk, don't digest it well, but a lot of people can, because it turns out it's really super useful in a lot of evolutionary scenarios to not die. And eating milk is one of those things that helped us do that. So, I mean, the ability to eat milk has evolved separately like 3 times in the human species. Like, it's turned out to be really useful. And if you were not, eating a fruit popsicle and eating an ice cream cone, then we could have gone to Jon to demonstrate that. But sadly, no.
But the diet industry is such a bizarre one, isn't it, that we people keep falling for it, because it is really simple. And I know most of us fail on this if we have this, which is just eat less crap. If you just notice that if your vegetable bin is going high very, very quickly, you go, oh, that's good. That must mean that I'm eating a lot of vegetables, because there's a lot of carrot tops in there and there's all those different things. And that's it, really, isn't it? I mean, it's a reasonably simple thing. Basically anything that keeps you from not dying. And really, scurvy, rickets is something that's actually coming back in the human, species. So we get more and more cases of rickets, even in, hyper-modern, well-fed populations. And so, you try and get your vitamins and nutrients. It's pretty much very difficult to starve to death.
There's a lot of vitamin C in here, I think.
Yeah, that's very much. They've been available on the bounty. There'd never have been a mutiny. It's as simple as that.
No scurvy news.
I hope you're brushing your teeth afterwards, or you're going to end up like Robin, though. So
during during the show, that's what we need. This is another diet-based question. I'll start. I don't know who's going to be the best on this one, so I'll start with you, Helen. This is from Spiderfish, who wants to know: can I burn more calories by thinking intensely rather than not? And this is something that always interests me, which is we're told how many calories are burnt by, and I know a lot. There are people who seem to think almost nothing, whereas a lot of people I know really concentrating on a lot of ideas, reading a lot, researching a lot. We should surely be able to see some sense of benefit from that, from their physical appearance.
So the caveat here, I guess, is that none of us are neuroscientists. We know that the brain is a very energy-intensive organism, but the thing is, it's doing quite a lot of things anyway. So brain neurons are firing all the time, whether you are consciously thinking or not. Quite a lot of your brain is not involved in conscious stuff, right? It's busy keeping you alive. It's the bits on the outside that do the conscious bit. So this is very much me not being a neuroscientist, but my understanding is that, first of all, your brain is doing a lot of things all of the time. Whether or not you think you're thinking, it's very busy in there. And so even if you did have a bit of extra blood flow because you were thinking about something, that's like it's a relatively small amount around the outside. But other than that, I'm not entirely sure. But I think just keeping it ticking over normally is probably where most of the calories because your brain still uses calories when you sleep, for example, because it's organizing things and doing all this stuff when you're subconscious, not conscious. So I suspect not. I would recommend going for a walk instead.
See, that's a pity, is it? Because I like that. People, the end of Christmas always go, do you know what happens? Every January, I join the library, and then about 3 months in. But of course, the great things about libraries are they are free, so you don't have to, unlike a gym. And so support your local library whenever you can in this.
But if you can think while you exercise, that's That's the other thing. I mean, I do a lot of sport, clearly, but it is very, if you do a lot of sport, it's good for you in lots of ways. And you have ideas when you're out exercising because your brain's, not thinking about other conscious things. And so you win both ways if you exercise. I think that's a good thing, even in the heat. Maybe go in the morning when it's cool.
And try and think thoughts about the nature of the universe and the curvature of space-time while doing your kettlebells, and everything will turn out well. This is from Klaus Kinski, not that one. I presume not that one. Otherwise, we're going to be breaking, I think, the second law of thermodynamics by getting a message from the late Klaus Kinski. But this is, I'm going to throw this to you, John. Has modern science really not figured out a way to deny Anton Lavoisier's law of conservation of mass? Can we really not yet turn somethingness into absolute nothingness?
Well, I guess that the answer is yes and no. Yes, we can. The Lavoisier's law. Yes, we can violate conservation of mass. Mass is not a conserved quantity. On the other hand, we cannot turn somethingness into nothingness. So you can annihilate matter and antimatter, or you can fission a nucleus or fuse nuclei, and what you end up with weighs less than what you started with, or more than what you started with. So mass is not conserved. It's conserved in chemical reactions to a very good approximation, although actually that is an approximation as well. Because we actually know the thing that is conserved is energy, and mass is actually a form of energy. So you can shift your energy around just the same way that you can shift potential energy into kinetic energy by, when something falls and it loses potential energy and picks up speed, which is kinetic energy. When you undergo a reaction, let's say a nuclear fission, or you can break a heavy nucleus up into smaller nuclei, and the sum of the mass of the smaller nuclei is less than the mass of the initial nucleus. So you've liberated some energy, which typically would be kinetic energy of the fragments that are flying away. So you don't conserve mass. But even if you take some antimatter and some matter and annihilate it, you do still conserve energy. And typically, I mentioned the electron-positron collider before. That was colliding matter and antimatter, electrons and their antiparticles. It was annihilating them, but it was very far from just vanishing them away. So when you annihilate them, all the energy that was in their mass and the energy that was in their kinetic energy, in fact, in this case, was available to create new particles. And that's what it did. And often they're photons, so they're not what you say matter particles. They have no mass themselves, but they still have energy and they're still there. So we know how to transmute elements, we know how to destroy and create mass, but we never turn something into nothing because we're always conserving energy. We can never get rid of the energy.
Thank you, John. This is for you, Brenna. This is we need a kind of statistic here, which is basically on how often when you're digging does something that looks like it's going to be wonderful end up just turning out to be another bit of old tat. And I wonder about how your eye and your understanding of objects manages to find itself. So eventually you go, 2 years ago, I'd have seen that and thought, no, I haven't. And how much you are ready, or whether that's just a kind of level of archaeo-pessimism.
I'd say that pretty much like every other branch of scientific inquiry, it's a question of managed expectations. But the thing is, you learn to stop worrying and love the crap. You just decide that the old tat is just as interesting, which will take you much, much farther. So it turns out, the question I always get asked is, what's the most interesting thing you've ever found? And what people mean is, what's the coolest, fanciest object? In which case, it is a small amulet of a goddess with a fish for a hat, which was fascinating. And I found on the body of a 13-year-old-ish girl outside the pyramids of Egypt. So that's neat. But most of my time is actually spent doing things like staring very intently at the ground for little tiny, smaller than my fingernail, bits of obsidian, which are tedious and horrible and really difficult to see. But if you find enough of them and you carefully map them and you carefully plot them on a big landscape, you can actually see where little groups of Cretan hunters were charging around on this stupid abandoned island, trying to hunt these goats that they kind of seeded the island with 5,000 years ago. And that's cool. So you start changing your idea about what cool is.
The way you described your discovery in Egypt, you made it sound more like you were street thieving off a poor child tourist rather than actually doing archaeology.
Isn't it that waste is actually really interesting in archaeology? So on the Thames, for example, by Greenwich, people built that on rubbish. Like they used actual waste from London to build out the bank in order to put a building there, and then they basically made it out of rubbish. And the archaeologists love it because it's kind of washing out into the Thames as time goes on. But it's not quite as organised as the teeth. But the waste tells you the stories, and yet they used it as a building material. They were reusing their waste, so it wasn't useless even to them at the time, and it's still carrying its story with it.
And all of our sort of gardens here in London, or the parks and stuff, they're all built on big masses of sort of landfill that's been moved around. So they're bits of clay pipe, the cigarette butts of the Victorian era, yay, bits of broken glass, brick, everything. And if you pile all that up and you actually get someone to sift through it, it tells a story. That's what we're supposed to be doing. At least I think that's generally what we get paid for.
John's
quite correct. Calvin and Hobbes, which, as we know, is if it's only one philosopher you're ever going to read, then read Bill Watterson, because Calvin and Hobbes is always. I mean, it's still one of my favourite things. That scientific progress goes boink. I think is if you're going to get a tattoo, John, please get that tattoo. If you haven't got it already, of course.
I couldn't show you.
Let's see. Right, this one is because you were in Greenwich a moment ago, Helen. This is, I suppose, it's more galleon than clipper based. But John would like to know: is it possible that increasing acidification of the oceans could corrode sunken Spanish treasure? And he also says, if you know where it is, could you not broadcast it but message him?
We generally, in general, people are very close-lipped about where treasure might be. There is a genuine major problem with treasure hunters in the ocean because it's much harder to spot what people are up to. If a boat's just hanging around in an area for a while and you don't know there's a site or a shipwreck underneath it, there really is a problem there. Corrosion, right. So the first thing about ocean acidification is that it isn't making the ocean acid, it's making it less alkaline. So this is the partner of climate change that no one really talks about as much as I would like, which is if you put more carbon dioxide up into the atmosphere, quite a lot of it ends up in the ocean. The ocean's doing us an enormous favour, but what it does, it changes the chemistry of the ocean. So the ocean would normally be 8.1, or it was 100 years ago. Now it's 8.05, so it's become more alkaline. So it's not acid yet. And frankly, if it does become acid, we have so many other problems that we are not going to be treasure hunting at all. But that tiny change in pH, which is reasonably evenly distributed over the surface waters of the ocean, makes it risk is it makes it a bit harder for calcium-based things to live. And the problem is that they are the base of the food. The equivalent of plants on land come in two forms. One's calcium-based, one's silica-based. And if you have a less alkaline environment, it makes it harder for those to grow. So basically, by the time you've got to the point where you might potentially dissolve anything that came out of a Spanish galleon, you have already killed off at least half of the entire ocean food chain, and that produces at least half of all the oxygen that we breathe. So and actually it happens naturally in some places where there are underwater volcanoes. So because they produce carbon dioxide, there are places in the Mediterranean, for example, where you get a little sort of not a full-on volcano, but it's the same geological structure. It's producing carbon dioxide, and so you get a localized region of slightly more acid, less alkaline water. And even then, I don't think it's really acid. Rivers are a bit different. This actually goes on for a while. But so basically the short answer is I wouldn't hang around to get to that point, because we'll have so many other problems that no one's going to be looking at the archaeology. Even Brenna won't be enthusiastic enough to be looking at the archaeology if we get to that point. And no, I'm really sorry, I don't know where any Spanish galleons are. But again, it's actually the same with ships. Most of the really interesting and valuable stuff isn't the gold. Everyone's focused, the treasure hunters are focused on the gold. The archaeologists are after the stories. And that's why the treasure hunters are really annoying to the archaeologists, because they just pull things apart until they find the gold bits, and in the process you lose where everything was. So don't go treasure hunting underwater. That's a serious thing. I'm really sorry that it's boring, but please don't do it.
It is also prosecutable in almost every country, so I'd add that.
Not recommended.
Overall, a jolly question became increasingly bleak. That's good. That's what science is all about. If science is about, it's why it's making me so hard for me to write this book, which is saying that the scientific picture doesn't add any kind of bleakness into our finite existence. But don't worry, you're all battling very hard to prove me wrong. This is the next question. I like this question. This is John. This is for you. This is the Large Hadron Collider. Which is basically, is there a build-up inside the LHC of things like proton dust or small piles of neutrinos and other atomic detritus? It's a rather beautiful image there.
Yeah, no, I like that. So, not neutrinos, just they're so light, they travel as fast as light and they go through anything. So they just zoom away as soon as we make them. And protons have electric charge, so they're quite easy to pull. The magnets can manipulate them and get rid of them. What the nearest thing to that I can think of actually is neutrons. Kind of tricky. So, neutrons, especially slow neutrons, actually are quite nasty for things like your electronics, and we have very sensitive detectors there, made of silicon and stuff. And it turns out neutrons do get produced quite often in these big collisions. Often as secondaries, not in the primary collision, but just as particles bash through everything around them. And they behave like a gas. So you essentially have a gas of neutrons that can kind of float around inside the LHC. And it will hang around most of the things. You turn the LHC off and within tiny fractions of a second, nothing else is happening. But this gas of neutrons is still floating around. And for a while, I was working on designing a detector that would be 450 meters away from the collision point. And we were wondering what the particle backgrounds might be, what stuff it would see as secondaries from the collisions. And pretty much the only thing that got there was this diffusion of this gas of neutrons down the beam pipe, which was kind of annoying, but also quite. I don't know. The idea of a gas of neutrons I quite like. They also decay after about 9 minutes, if I remember rightly. So they don't live forever, but they're the longest lived bit of particle rubbish that hangs around, I guess.
Particle rubbish. That's a lovely.
I love the idea of someone having a Hoover. I mean, I know that's not quite how it works, but a neutron Hoover. It's like the cleaner comes round. Get out! We've got to Hoover under the desks because the neutrons are getting out of control.
Well, that's what the carbon rods are in the reactor. But yes, we tend to keep the cleaners out and just let the neutrons decay, and then the cleaners can go in when they've gone.
And if you would like, there's a lovely illustration of coming on having miniaturized cleaners in the excellent Viz comic strip Tiny Cox. If you've not seen it, it's a Brian Cox based spoof. I have to say that Viz do some of the funniest Brian Cox cartoon spoofs. I keep telling him to buy the original artwork. They are absolutely fantastic, both incredibly childish, but from a childishness that can only come from a level of understanding. It's brilliant. This is, by the way, John, just to warn you, someone wants to know exactly what dark matter is, so just start preparing yourself. But on the plus side, no dark energy. So I know that's not right. I know we're going into a totally different scale for you, but that might, with luck, I'm going to find enough questions that we'll never actually get there. This is Helen. What makes noise? This is what Angela would like to know, as in when I clap my hands, why is there a sound? Is it atoms banging together, or is that like when my mum used to tell me that thunder is clouds bumping together?
Clapping is quite interesting because you generate a mini shock, which is not what most people think of when they think of clapping, because we associate shock with big explosions and stuff. In general, what generates sound is anything that moves air. And obviously sound can travel in liquids and solids as well. Basically, if you move it really quickly, because of the way matter works, after a while it becomes waves, and then you can detect those. You can detect that vibration. So what your ears are doing is detecting the sound, the air doing this. In the case of a clap, I'm a bit nervous to do one directly above my microphone. But what happens, and you can actually see this. There's a very clever kind of imaging called Schlieren imaging, which lets you use mirrors to see density changes in air. So if you clap,
how would you? Because how does that? So people want to look that up afterwards. What's that imaging called? What's the actual?
Schlieren. It's SCHLIEREN.
Okay, cool.
And it's a way of you get these. It's really fiddly to set up, but you get these beautiful images of shock coming out. And the reason you see the shock is that there's a density change. So air does. We think of glass having a refractive index. That's why we put it in glasses. But actually, air has a refractive index as well. It's just only a tiny bit above 1.
Helen, aren't these the same images that they've used to show how masks work, actually? When you see the Is that the same thing?
It can be used for that, yes. So you can see density changes, yeah. But if you use that for the clap, so yeah, you can. I'm not sure whether they're all that. That's why I'm hesitating. But if you use it for a clap, what you see is that basically, as you cup your palm ever so slightly, and as the two cups come together, air is basically forced out through a tiny gap, and it rams into the air around it, and that pushes on the air, and that's what travels out. And the reason the clap sounds really sharp is that basically the density change is so great. It's basically like a hard wall hitting the air on the outside. And the reason that some claps don't work very well is that if you let air escape out of other gaps, so in that sort of that kind of thing, right? If you let the air escape, if the shape of your hands lets the air escape in too many places, you don't get a shock, so you don't get that sharp noise. That's the thing that makes it a sharp noise rather than just a loud thing. And it's a weak shock, but that's the distinction. And on Schlieren imaging, you see really clear this little front coming out that spreads away, and then it sort of becomes normal sound, and the density variations change. But basically the world is a musical instrument. I mean, everything around you is a musical instrument that makes a noise depending on its structure, and all you have to do to hear the structure of something is to basically, it's like a hammer hitting a bell. You just need to apply something that makes the structure move, and in the way it moves gives away what it's made of and what shape it is and how heavy it is, how much mass it has, and that's what you hear. So sound is very specifically hearing structure. And there is an ice cream van.
I know. I was just saying how annoyed John is, because John already had his orange lolly. He could have had another one now, couldn't he? Too late, John. We're going to have a Mivvy instead. Bad luck.
But what you're hearing is a physical structure inside the ice cream van, although now they tend to be electronic. It's electronics mimicking a structure, but it's still, you're hearing a structure, you're hearing it do something.
It is. There is something. I never that moment when you sometimes think about what is required when you're hearing music, for instance. That if you're tuning into an old-fashioned radio and you think there's radio waves there, they're all around me now. All we need to find is the receiver, and then once I place the receiver, then I have those vibrations going through there, which suddenly make variations on a theme by Thomas Tallis, by Vaughan Williams, or whatever. All of those bits. When you stop and you start trying to see how you sense the world and all those possibilities,
there's something. Yeah, well, I was just going to add. There's another really interesting, just everyday example, because the one thing is generating the sound, and the other thing is that some things amplify it. And just as one example, so the wheel of a car comes up like this, and there's noise generated down here, and this shape, the road there, and the curve of that's like the horn of a trumpet or the horn of an old gramophone. And so the amount of sound that's made down here isn't actually that much that we could hear, but that horn shape amplifies it. So cars are actually the tire noise is louder directly in front and directly behind, because this horn shape amplifies the sound that you get. So sorry, I interrupted your musings about radio.
There was every point there
was matters as well,
but that was all made to be interrupted. Now, John, by the way, good news. I'm not going to force you into cosmology. We've had a quantum-based question, so you can relax now in terms of looking up dark matter on Wikipedia. But before we go any further, with Brenna, we've got a leprosy-based question. Let's just know about, which is why is leprosy considered the poster child of diseases amongst archaeologists? Now,
we love a bit. We love a bit of leprosy. Love it. So leprosy takes so long to kill you. I mean, just so long. The vast amounts of, possibly not historically, but probably also historically, most people who die with leprosy died of something else. Leprosy is a disease that sort of gets into your bones. It starts cutting off essentially circulation. You get something called tissue necrosis, which is interesting, but I don't recommend it. Your nerves basically die off. You lose feeling in your feet and hands. You start snagging them on things and getting little infections, and then those get into the skin. And so your feet and your fingers and various other extremities, they kind of start falling off. Leprosy. That is something we can see in the skeleton. So there are very characteristic changes that have to do with basically how that bone in the tips of your toes and your fingers starts getting eaten away, which allows us, the diggers, to identify leprosy as the actual disease that you suffered from. What we're not necessarily doing is finding out what killed you. So most people who die with leprosy today actually die of tuberculosis, which it turns out is the same bacterium sort of family. And one of the interesting things that people think, actually, is that one of the reasons we don't see as much leprosy as we do today, as we did in, say, the 14th century when it was all the rage, is that being exposed to tuberculosis might provide some sort of slight cross immunity. So the sort of party that tuberculosis created when it sort of crashed across the globe might have actually been a little bit protective against leprosy. Sort of jury is still kind of out on that, but you should basically be thankful that something that kills you quickly and horribly has stopped you from dying a long, slow, possibly not quite death.
Yeah, but your enthusiasm for is slightly worrying, I have to say. Like what that question at the start about the archaeologists of the future, basically they have to hope that, I mean, we don't want to know whether COVID kills you slowly, or we don't know yet what the long-term consequences are, but it was really worrying how enthusiastic you were about lingering.
This is professional hazard. So I mean, the problem is that obviously we want evidence. We want evidence of what's happening in the past. And if it doesn't affect something that comes down the line, then we never have the evidence. So you have all these horrible sort of things where, like, probably there's all sorts of stuff going on in the past that we just don't know about because they built it out of wood or they made it out of skin and it all disintegrated.
Those rubbish people who made things out of
organic, recyclable, completely sustainable lifestyles. How dare they? It's really inconvenient.
Is it just on sustainability? Should the aim of a sustainable society be to leave no trace that following generations can find? Because presumably, if almost by definition, if you leave anything behind, you're not being completely sustainable. So, if
you look at any major European city, the thing, like, after the sort of basically after pottery is invented, it's all downhill. There is rubbish everywhere. Anywhere humans have been, they have trashed the place for thousands of years with just bits of ceramic everywhere. And, the Anthropocene has been going on for some time. So there's kind of a strong argument to make that we used to sort of not mess up the environment nearly as much. But, then we wouldn't have invented things like CERN. So, obviously, trade-off.
Well, get away from the grotesque world of biology to the much more lovely world of physics with the live question from Roger. By the way, the other live question we had quite a few of. The answer is his name is Baloo. There we go. And but what Roger would like to know is, what is it, the thing about light not experiencing time at all? So this is something this is an interesting, I think we talked about this before, where when I was talking to, on a slightly different thing, but about that point where something doesn't experience time, that first 10 to the minus 37 of the existence of the universe, when we say 10 to the minus 37 of a second, actually saying a second doesn't kind of count because it may well be a period of time without time, which is kind of crazy, so go off in any direction you wish with this, emit yourself in any way.
Right. So I think the issue with this is the word experience, because light is not a form of matter. Light is an oscillation. It's a quantum of electromagnetic energy. So it's as I mentioned before when we were talking about underwater sensing, it's an oscillation in electromagnetic fields, and it's the quantized version of that is a photon. Okay. That may sound like a pedantic place to start, but actually that means because it's not matter, you can't have any structure. And because you can't have any structure, it's very hard to talk about a world made of photons or an organism that could actually experience traveling at a photon's speed. So the idea of experiencing time from the point of view of a photon is not something, I don't mean that we can't do it. I mean that you couldn't really build a clock out of photons either in that way, because there'd be no structure. But it's true to say that the from the point of view of a photon, in the sense that has any meaning, all points on its path are at the same time and simultaneous. So the way the relativistic equations of the Newtonian mechanics is a kind of low speed approximation of, the way they are, they dictate that at normal speeds, for instance, and the momentum is mass times velocity. As you approach the speed of light, there's a gamma factor that you start to notice, which is almost 1 when you're miles away from the speed of light. But as you get to the speed of light, this gamma factor grows and grows. So the beams we have at CERN have a huge momentum, which is much more than the mass of a proton times the speed of light. But the beams are traveling at practically the speed of light, almost the speed of light. So the kind of equations you learn in physics up to A level, in fact, don't apply once you get to very high. They're very good approximations in everyday life, but once you get to speeds approaching the speed of light, they don't apply. That gamma factor, you still with me? Sorry. But that gamma factor has got a 1 over c minus v in it, basically. So as c and v, c is the speed of light, v is the speed of the thing. As they approach each other, that 1 over this number becomes 1 over 0, becomes infinite. Okay, and that means you've got essentially a singularity in the equations. That's where photons live. And the net result of that whole thing is that anything that has any mass cannot travel at the speed of light or faster. But less well known is actually that anything that has 0 mass has to travel at the speed of light. It's not just light. If there was anything else that has 0 mass, if neutrinos had 0 mass, they would also have to travel at the speed of light, which is what we thought was the case until recently. So that singularity, that point, it's like being on it's time does stop at that singularity. Yes. So the photons do not experience time in any meaningful sense. They don't experience anything in any meaningful sense. But all points on a photon's path are at the same time from the point of view of the photon.
And thus they never experience nostalgia, the sadness of light. So thank you very much, Jon. Thank you very much, everyone. We had a question as well, which we're not going to get to this time. We've had a lot of stuff now on the live question as well about sound and about clapping. And so we'll do a Sunday Science Q&A, which will just be about sound. We'll do that in the next few weeks. And what are you doing? She's doing more of this magic, the creation of sound. Anyway, so next week, as I said, we're going to be doing it's astrophysics next week with Katie Mack and Jen Gupta, and Helen will of course be back again. And I will also quickly mention we don't like to bang on about too much, but if you can support us by Patreon or by giving something in the tip jar, it's kind of reaching the stage where it would be very, very useful to us. And I hope you're enjoying all the stuff that we do. We try and make as many shows as possible, and we have lovely people coming on. And I should also say all this kind of we've been doing this now since the Sunday Science Q&A, since lockdown began, and we've got a huge archive as well. They're all still up. You can listen to them in audio version, or you can watch them on YouTube with Brian Greene and Ethan Melissa and Alice Roberts and Brian Cox and lots of other people. All of those Q&As are still up, as well as pretty much all of the other things that we've been making. So if you can support this pointless endeavour, then please do, because it might even have some point to it underneath it all. You never know. Jon, quick question, by the way, from someone. When I first saw the Science Q&A was coming up, I thought it said Jon Shuttleworth. They're interested to know how often you, Jon Butterworth, are booked, and then they're a little bit annoyed that you haven't actually turned up with an organ and a selection of songs about the Snake Pass. Not happened yet, but I live in hope. Okay, then. Well, I hope that cock up happens at some point, because I think Jon Shuttleworth will also have a very interesting take on the Large Hadron Collider as well. So thanks again. Thanks very much to Trent Burton, who produces this. I said we're back next week. Please try and support this stuff. Go and look at all of the people's work that I mentioned before. Brenna's latest book, Helen's latest book, and Jon's latest book. And we will be back in the week with Show and Tell with Jay Wilgoose, and there's some more book shambles coming up as well. I think next week we have the person who is currently, or they might be not anymore, but was top of the New York Times bestseller list. Go to our website and find out who I'm talking about. There's lots of other stuff at the website as well, of things that we've got coming up and things that we have done. Bye-bye.